Good morning. Today we will look at boiling. But before I get to boiling, we'll just quickly overview what we have learned in convection. I'll spend a few minutes saying that how is it that we got data for the fluid flow heat transfer problems that we have seen in forced and natural convection, and then we'll go on to boiling. So to summarize what all we have learned, we can classify all the problems in 4 categories. They could either be natural convection or forced convection, so that are these 2 columns, and that could be either external flow or internal flow. And we saw several examples of natural convection. External flow is a flat plate in a large fluid, or a cylinder in a large fluid, or a sphere in a large fluid. Natural convection internal flow, we looked at enclosures through which there is a fluid subjected to a temperature gradient. Under forced convection external flow, we looked at flow over a flat plate, we looked at flow through tubes, flow over cylinders. And forced convection internal flows, we saw flow through tubes, flow through ducts. And we came across many applications of each one of these in engineering. And what we learned in all of this is finally, what is the relation between the heat flux at the wall and a sort of a temperature difference between the fluid and the wall. And this relation got completed when we added the constant, or the thing that equates these two, is the convection heat transfer coefficient. And this could be the local one, which is over a small area, or the average heat transfer coefficient. Average because we have said that it will apply over the entire surface, that somewhere there could be a locally high heat transfer coefficient, somewhere there could be a locally lower heat transfer coefficient. So this is what we learned, that finally H depends on the fluid dynamics of the flow. And we came across the differential equations by which we could solve them. I also mentioned that in many cases where the equations are not possible to be solved, we do a lot of experiments, and based on experimental data, we develop the answer for H in the form of a correlation as this as a function of, say, Reynolds number, or yesterday we saw Grashof number and Prandtl number. And this is the solution to those conservation equations, which we use, and in the non-dimensional form, we can use them in a variety of problems, and that is how we solve problems. As time goes on, better and better correlations come up, and one could use those. If the geometry is complicated, then you have to have a correlation for that particular geometry, and that is used in that particular case. So there are many of these available, and we have to realize which of these to correctly pick up to solve the problem at hand. So that's what we had done. And now I'll contrast that with what's going to come up now in boiling, and then later on in condensation. Both boiling and condensation are phenomena where there is a phase change. And that is why it is different from what we have learned so far in single phase transfer, that if we had a liquid state, it was a compressed liquid, which before and after heating remained a compressed liquid. If it was a vapor or a gas is nothing but a highly superheated vapor, then after heat transfer or by heating or cooling, it remained a superheated vapor or a gas. So we did not consider the situation where that fluid ended up changing its phase. Boiling and condensation are exactly those phenomena where there is a phase change. And to look at that, we will quickly visit something we have learned in thermodynamics, and that is the TS diagram. Okay, and what we saw there is all types of convection heat transfer in the gas phase, they were lines that were going like this. Say a line over there. That would be a cooling line. Or if we pick up this line, this could be for heating. And the line follows the condition that the pressure does not change during the process. That's what we had done all the while. The second case, which was the heating and cooling of a liquid, falls in this tiny little region which we cannot even see there. But if I blow up a little bit of this part, that this is the saturation curve and this is the line over here, which is the 100 megapascal bar, then the heating process which follow constant pressure, they will follow pretty much like this. So everything, the begin and end points of the process are within the compressed liquid state, and here the begin and end points are all in the superheated state. Well, what happens if we follow this line? So it started from a compressed liquid, and somehow we say that it ended up in superheated vapor. But because the pressure is greater than the critical pressure, we do not see a phase change. It goes from being, say, a compressed liquid to being a supercritical fluid, or some would call it a superheated vapor. Well, in this case, we would still apply the principles of single phase convection, what we have learned so far, but the relations that we have developed would have to be applied with a little bit of care in this part, and there are specialized correlations specifically for supercritical heat transfer. So we will have to use those. The difference is that as it goes from here to here, there is no discernible change between the liquid and the vapor phase, which is what we see in boiling and in condensation. So that doesn't happen here. Where is this important? In supercritical thermal power plants. Most of the power plants now being put up in the country, the pressure is more than the critical pressure of water, which is 220 bar. And so you do not have any distinct region where you say, now this is where I will do phase change, this is where I will do heating of liquid, this is where I will do heating of the vapor. So when we design heaters which are all, or condensers which are below the critical pressure, here is what we end up have to worrying about. That it's the process would start here and say we got it up to this point. So this was heating a liquid, which remains a liquid. Then we go that way, converting the saturated liquid to saturated vapor, and then we go there to produce a superheated vapor. And the opposite would happen if you were doing cooling. Now what happens here in the design of the equipment is that we say, well, how do I design this part? And when we look at all the correlations that we have learned, we find that this particular region has a certain heat transfer coefficient, and a certain area is required to effect this heat transfer. And because it is a liquid phase, we design this section separately. Then we look at this phase and say, well, I only have vapor in this region. And if you look at the correlations that we have, in general, vapors and gases have much lower heat transfer coefficients than liquids do. So this part of the heat transfer process has to be designed very differently, and this may require a much larger area than this would have required. And then we say, well, what happens during this process? When I go from saturated liquid to saturated vapor, we are having a phase change taking place. And so what's going to happen is what is the variation of heat transfer coefficient here, and how much area do we give for this? So this becomes a third heat transfer problem. So what was there as a thermodynamics problem in the heat transfer part becomes three things in sequence, one after the other, where we provide this particular design for heating the liquid to saturated liquid state. Then we provide a region where we convert the saturated liquid into saturated vapor. So dryness fraction 0 here, dryness fraction 1. And then we design another part of the device which will do the heating of the fluid from saturated vapor state to superheated vapor state. And that's how, whether it's a boiler or whether it's a feed water heater, we end up designing everything as 3 series heat exchangers which do this job. We have learnt about this, we have learnt about this. Now we will look at what happens here. The opposite of this process happens when you take superheated extraction steam from the turbine and then put it down and cool it in the feed water heater. So first we have to design a section which desuperheats that vapor. Then you design a section which condenses that vapor to saturated liquid. And then we have a region where we further subcool the liquid. So again, the heater design follows three principles. If it is a condenser, then it could be slightly different in that the exhaust steam could be already a wet steam, and our objective is to just condense it and bring it back to a saturated liquid state. And this only means that you need to design one thing for designing the condensation of the liquid. So the condensation part we will look at tomorrow. Today we'll look at the part as to how do we get a saturated liquid to become a saturated vapor, and that is called boiling. So when we look at boiling again now, we could have again the four combinations that we had for convection heat transfer. We could have natural external flow, natural convection boiling, external flow, forced convection boiling, internal flow with natural convection boiling, and internal flow with forced convection boiling. And in boiling, again, we pose the same question: what is the relationship between heat flux at the wall and a temperature difference between the wall and the fluid? So the first thing that happens in the case of boiling heat transfer is that both boiling and condensation is that there are some very fundamental differences in the whole approach. And I've listed some of these points over here. What it tells us that in single phase flow, we had only a single fluid, which is like a continuum. Everywhere it was homogeneous, it was in the same phase, and we could consider it as one particular substance. But that doesn't happen when you have phase change. Somewhere you have, in the case of boiling, somewhere you have a liquid. When it changes phase, it could become a vapor. So you have to deal with vapor and liquid both in the saturated state. In condensation, you have to deal with again vapor with liquid in that. So there is a problem. We do not have a homogeneous fluid which we are trying to analyze. It has two components, two phases, which although individually are a continuum, put together they do not actually become a homogeneous continuum at all. This has very far-reaching implications on writing the equations and trying to say, I will write the equations and solve the problem. Very few simple cases have been done using supercomputers, but engineering is still relying on doing some experiments, getting some numbers, and designing the machine. The next thing is, in convection heat transfer, we drew a fluid element. And I said that it could be a cube, and we took for all differential equation analysis a cube and then figured out what goes in and what comes out of this. Now we have to worry that, well, if I do not have a continuum, do I have a drop in there or do I have a vapor bubble there? And if I take this element, what do I have in it? How much liquid, how much vapor is there? This is a really big complicating factor, and this could change from place to place as well. So this makes writing the equations of the conservation equations for the fluid itself becomes a very dicey proposition. One cannot say with any degree of confidence that this is the equation that governs this type of a flow, and if you can solve it, you will get the answer. That doesn't happen. So there's a complexity which has come in writing the conservation equations. You have two phases doing funny things with each other. Their shapes are not perfect. They vary from place to place, and it's absolutely impossible to say what is the governing equation for this. Then we need the boundary conditions to define the problem. And fortunately, here we don't have too much of a problem in that we say at the wall, I have certain temperature or a certain heat flux, and rest of the fluid is at its saturated state. That much is known, but not much used because we don't know what equations to solve. In single phase flow, the fluid was homogeneous. Here we have heterogeneous fluid, whose composition varies from location to location. And finally, all the things that we looked at in convection heat transfer, we said they were in steady state. Even though turbulence is inherently unstable, we still said that if you take a long time average, you would still see an average behavior, which is why we drew those velocity profiles inside the tube or the boundary layer profiles for turbulent flow. So we made that into a sort of a quasi steady state situation and said, look, those are time invariant things that happen in single phase flow. Well, in two phase flow, the process itself is not only inherently time dependent, but very hugely random. So you have to now really have to worry, what do I do with this? Where at any instant of time, if I take a picture of boiling or of condensation, I'll see something different happening there. So where is my equation going? So these are all the complexities that come in, and the bottom line is that the relation between q dot double prime at the wall and delta T, which is the difference between the surface temperature and the fluid temperature, sometimes we call this the excess temperature. We do have some relations, but they are entirely based on experiments and limited by the experimental setup that one was working with. So we get into a very difficult proposition of how you get this, and how do I say what is the average heat transfer coefficient for that problem. And because we do experiments in a very limited setup under limited conditions and then extrapolate it to different conditions, so it would be nice to say, well, what are the non-dimensional ways in which this data can be extrapolated? That is the thing we would like to do. The trouble is, after doing all of that, uncertainties in heat transfer coefficient in boiling and condensation are very large. I had mentioned that in single phase convection, uncertainties of plus minus 5%, plus minus 10% are normal in most correlations. Uncertainties of plus minus 20% are not uncommon, but in boiling and condensation, uncertainties of plus minus 50% can be expected. So we have to be very careful in dealing with what we have and take that number in a very careful way when we actually do the engineering of the device. So this is something that is still a big issue, and there's no real simple way to say that how can I get a more accurate number for the average heat transfer coefficient. So please keep that in mind, that whatever we have learned here and whatever we are doing by way of all the correlations, we are living with a world of uncertainty, and we have to always be careful about that when we interpret the answers and the results in any engineering device. Okay, so having said that, let's come to boiling. Oh, sorry, before I come to boiling, let me just give you a few ideas how we develop of a probe that is used to make velocity measurements in an air flow or a gas flow. This is called a hot wire probe, and what you are seeing here is a base there whose size would be of the order of like about 5 to 8 millimeters. On top of that are these prongs. They are coming out, they are coated with gold, and a pair of these, you can see there is a wire connected between them. This is a hot wire, and like this you have 3 wires which are at mutually perpendicular to each other. And what this probe does is that when you put it in the flow, you get the wires are very, very thin, of the order of 5 micrometers in diameter. The human hair is about 100 micrometers. So they are very, very thin. How we make it is quite an interesting thing. And this is a basic tool that one uses to make point-wise measurements of velocity and turbulence in an airflow. So all the data that I was talking about of what was how mean flow changes and how boundaries are developed, one used this in the case of gases. This is a technique where we get a dye which you can paint on a surface, and the dye changes its color depending on the temperature. The picture I am showing you here is a very thin film of plastic on which this dye has been put, and at room temperature its color is black. So when you put your hand on it, the hand is warmer than the room temperature, and you can see this entirely. You get a complete thermal map of the skin temperature in this particular case. So this is a very nice technique by which a complete map of the surface temperature can be obtained. A fairly high-end heat transfer problem, and what you see is all these small, nice, colorful pictures where what they did, they took a surface, they drilled holes in it and put air through this, and they have coated the dye with the dye, the surface with the dye, and here you can see different ranges of color and tells you where the surface is hotter, where the surface is cooler, and from this you can very also qualitatively figure out where the heat transfer coefficient is really high, where it is low, and how it distributes itself on the surface itself. So this is a very powerful way of getting information. The other techniques include, okay, so we leave that. That is an idea to give you a flavor of how experimentation takes place in convection heat transfer, and how we get data and we analyze it and use it. Now we come to boiling. So we are looking at phase change, and here we are looking at phase change, and we say that 2 possibilities can happen, that we have a saturated liquid which is heated and it becomes a saturated vapor. So in thermodynamics, we can say that this was x is equal to 0. This is dryness fraction x is equal to 1. So thermodynamics is coming in a big way now, and we can see that. The energy required to take it from here to here, we have already learned that this is HFG. The second possibility is that we could have a subcooled liquid, and there we are boiling it to produce a saturated vapor, or you want to call it a dry saturated vapor. The degree of subcooling may not be very large, 1 or 2 or 5 degrees, something like that, but it is still a subcooled liquid, and you can see that by heating it, we are producing a dry saturated vapor from the substance. So both these are possible. Most of the correlations we will see are for this particular case. Saturated liquid being heated to form a dry saturated vapor. And like all heat transfer process that we have learned in convection, in the engineering part, the assumption was that in all those cases, pressure is constant. So it's an isobaric process. And if you recall heat transfer thermodynamics, when you learned that, whenever we were talking of heat transfer, we were always saying that the heat transfer is a constant pressure process. And this is the reason why it is coming out from here. Here also, we will assume that in pool boiling, when we are converting this, doing this phase change, pressure is constant during the process. Okay. How does heat transfer take place? Well, we have a surface, and this could be any type of a surface, we'll just come to that in a minute, whose temperature is higher than the saturation temperature at that particular pressure. So very simply, we can say that we have something in this. We have somehow managed to maintain in this a saturated liquid, and we put into this a heater, which we have pass current and heat it up, so that the surface temperature of this is what we have called T surface or T wall. This is greater than the temperature over here, and something happens, and finally a big player in this is gravity. Whether we acknowledge that or not, gravity is an important player, and finally because of that we start getting vapor from the free surface of the fluid, and we can say that the top of this is exposed to either to saturated vapor, or to say, like if you're boiling water in a pan, then this would be subjected to air into which this vapor is coming out. So that is the first thing that is happening, that we need to quantify what is the surface temperature. The very fact that boiling occurs means that the pressure is less than the critical pressure, and to be very precise, we can even say this is greater than the triple point pressure of the substance. It is only between these two pressures that a phase change can be seen, as thermodynamics has taught us. So now the question is, what do we see happening at the surface? And I'll show you a few pictures in a minute. But if you have taken a pot of water, put it on a gas stove or an electric heater, and then put it on, and you keep observing what happens in it, you will see that you can sometimes see water moving here and there, and then you can see some bubbles coming. It starts making a sound like tick, 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 and then you can see a lot of bubbles coming out, and then the whole thing is boiling over like that. That is what is happening, and that is what we are trying to study. What that process, if you see, does is that essentially it did form vapor bubbles at the surface, or the fluid got heated at the surface, something happened there, and it went up. And when it went out, it left the surface. A new bubble formed up. That put up 1 degree of randomness, that at any point on the surface, with time, sometimes there is liquid, sometimes there is vapor, sometimes there is a bubble. There are also times that if you look at another point, this may not be happening. So if you are boiling water in a pot, you will see that bubbles originate at certain points on inside the vessel and not everywhere. So those points that are where the bubbles are originating, those are what we call nucleation sites, and not the entire surface is covered with nucleation sites. So what we will do is we will look at what are the basic features of these types of problems and ask the question, how can I predict the relation between the wall heat flux and the excess temperature difference, that is difference in TW minus the T infinity or the T saturation that you may want to call it. So the saturated liquid, what we are calling as T sat, this plays the role of T infinity that we have looked at so far. Okay, so this is what we are going to do. I'll show you a few pictures of boiling and then we'll come back and see what to look at. Okay, these are taken from the internet, but there is no reason why we cannot make it in our own lab or in our own house. Here you have a transparent vessel made of glass in which water has been kept and is being heated from the bottom by a gas burner. And what you are seeing is here, if you observe, a small bubble is formed over there, almost spherical. Then you can see another bubble which is above this, another bubble which is here, then here, and finally it comes here, and there is a vigorous thing happening at the surface because these bubbles are bursting out. This is one example of what we call that you have a vessel which is full of liquid, and that is what you are seeing as a pool of liquid. So we'll come back to this and see what is the dynamics of this. So let's see what are the types of boiling that we encounter in engineering. Okay, so first is this very thing that I just showed you, which is what we call as pool boiling. And we have two possibilities of pool boiling. A vessel in which we have the liquid and we say that this is at T saturation. Above this there is air or there is vapor which is also at T sat. So you have x equal to 1 there, x equal to 0 over there. And in this case, what we can do is what you are seeing on the vessel we just saw is that we could heat it from below, either by burner or by putting an electric heater under this, and we are heating the surface. So the action is happening on the inside surface of this vessel, and that is where the formation of bubbles and everything happens. There will be some conduction resistance on the bottom that will all taken care of. We are going to say, well, what is the TW that is happening and what is the rate at which liquid is becoming vapor. That is what we are interested in. Practical examples of this is cooking, as we just saw, whether we are cooking rice or whether we are cooking dal or maybe boiling eggs. Everywhere we are essentially seeing the same process happening. Another example would be that if you have a very large pool or vessel in which at some surface you are heating it from the bottom, this is encountered in refrigeration and some air conditioning applications, but those are rather few. This particular thing about making a pool and understanding the boiling is how our understanding of boiling started several decades ago, maybe about 60-70 years back. This was the simplest thing to make. It was a logical extension from convection in an external situation, external flow condition, and so there's a lot of information available on this. But if you look at the practical applicability of how frequently I will see these, it is not very much. It's somewhat limited in its practical application. An application that is a little more frequent is that we do have a pool. So this is our saturated liquid. We are not heating the container anymore. This is say adiabatic in the ideal case. But what we have done in this is we have immersed in this a device or a part or a surface whose temperature is greater than the saturation temperature. So the boiling is now going to happen and the bubble formation will happen over there. They will rise up and start going out from here. So that's I've depicted a horizontal cylinder. It could be inclined also, it could be any other shape also, doesn't matter. And the other extreme could be that we just have a plate, a flat plate, a vertical plate, or maybe a horizontal plate, which is initially at a very high temperature or is heated electrically, and then we ask what happens at its surface. So this is where again bubbling will take place, and this is what we call the external natural convection case. And for this, there are many applications. Listed here, one is chip cooling. There are instances where the motherboard or the chipset in a computer is dipped into a fluid which will boil, in which the boiling will take place, and typically this is, say, refrigerant, one of the refrigerants. Okay, the second is the example of a fire tube boiler, where what we do is we have a big tank in which water is there, and it is contained in a shell, say like this. So there is water in this, and in this we put a tube which is opening across the two plates, through which hot flue gas is being passed. So now there is boiling taking place on the outside of this tube, which is something like that. Another example we would have come across is in manufacturing or heat treatment, where when we want to do quenching, we take a component, heat it up to a certain temperature, and then immediately we immerse it either into a pool of water or into a pool of oil. And in the case of water, you see vigorous boiling taking place. In some cases, depending on what oil it is, it could also burn, and maybe some amount of flames may also appear. So there are a lot of applications of this part. And what we want to know in the heat treatment process is what is the rate of change of temperature in the component. So that tells you what is the material transformation that has taken place, and that tells you what is it that you are going to get out of this particular type of a cooling process. So that was the example of external natural convection boiling. Now look at external forced convection boiling. That means you have a very large pool, and there is a surface on which boiling will take place, and this fluid is got forced convection is in motion. And an example of that is what happens in a boiling water nuclear reactor. It is called a boiling water reactor or a BWR because you allow water to boil. And where does the water boil? Well, you have a fuel rod in which nuclear reactions are taking place. Inside the rod, there are pellets of uranium where fission is taking place. That is generating heat. This heat is being conducted to the external wall of the tube and then to the water. So one class of nuclear reactors is BWR reactors, where you pump in almost like a saturated water, and as it goes over this, it starts forming bubbles, boils, and finally at the top you get vapor. This vapor is taken away and introduced into the steam turbine. So that's how you get a BWR reactor based thermonuclear power plant. The other, of course, other part is that you make a reactor where you don't allow boiling to take place. That means this water that is coming in is not saturated liquid, but a highly compressed liquid, and it exits not as a vapor, but as a compressed liquid. So you have avoided boiling in that type of a reactor, and those type of reactors are called pressurized water reactors or PWR. And then this water is taken out to another vessel where it is flashed, you get saturated vapor, and that vapor then drives the turbine. So there are two different technologies which practically cover almost all the nuclear power plants that are operating in the world, a BWR or a PWR. Here there is no boiling, and here boiling does occur. And this was one of the main reasons why there was so much research done on boiling heat transfer in the first place, that if you have a nuclear fuel rod on top of which boiling is taking place, we will see in a little while what happens locally where bubbles are formed, that there is a very high temperature and you could have really a problem there. So that's an example of external forced convection boiling. Now look at internal flows. And we say, what is the example of an internal flow with natural convection where boiling takes place? And the example of that is a boiler of a thermal power plant, especially older thermal power plants. What is done in these plants is that you have a drum, a boiler drum, in which we get a saturated state. From here, a pipe brings this water down and introduces it to the bottom of this tube. So here the water is saturated liquid or slightly subcooled liquid. So the saturated liquid comes in here, it remains a liquid, then it goes through this tube which is exposed to a furnace. So this is the wall which is insulated, and on this side you have the fuel being burned, typically coal being burned there. This is burning, this is giving heat transfer by radiation and by convection to the outside wall of the tube, And what is happening inside is that as the fluid here gets heated up, it begins to rise, and at some point it also starts to form bubbles. So what comes out of this tube and goes back into the drum is a mixture of liquid plus bubbles of vapor, or maybe vapor plus some drops of liquid. So you end up getting a wet state coming back into this drum. By gravity, the liquid sits down and the vapor is taken out, and then this is sent again for further heating. You have a superheater, and then finally it goes into the turbine. So the superheater design is based on the convection that we have already learned. It is a single phase heat transfer. What happens inside this tube is entirely by gravity, that you have gravity acting there, and because the water got lighter and the bubbles were formed, they rose up and finally went up. So the height of this tube is an important parameter in the design of these type of boilers. So this circulation of the water happens by itself, and that's why they are called natural circulation boilers. And this is only the case for subcritical boilers. For supercritical boilers, there is no phase change. We also have another application of heat pipes. What we do is we have a pipe and we fill it up a little bit with some refrigerant, which is at some temperature. This is liquid here, this is vapor here. And what one does is use this pipe so that this part of the pipe is in a hotter environment, and then the other part end of the pipe here, this is being cooled. So what is happening here is, because of this heating, this is boiling. It forms a vapor which goes up there, condenses, and comes back along the walls of this tube. So it's doing nothing but transferring heat from here to here. There's no work transfer involved in this, but the advantage one gets is that you get very high local heat flux at this point by doing this than what you would have got by single phase heat transfer. And that is one of the attractive features of boiling. That is called a heat pipe. It's been used in many places, including in some of the computer cooling chips. And the fourth combination that is now left is internal forced convection heat transfer, which is internal forced convection boiling inside tubes. And where do we see this? We'll see this in a package boiler where you have a tube. I'm just drawing the shape of the tube like this. And inside this is hot. Over the tube, we have hot gases which are produced by burning of flame. What came in was maybe subcooled liquid. What goes out is saturated vapor. So you have water going through this. It is being pumped, so it is a forced convection. It is being heated, and there is phase change. That's why there is boiling taking place. And finally, we get vapor coming out of this. So small boilers, they are of this type. Some power boilers are also of this type. We also encounter that very frequently now in all our refrigerators, air conditioning, evaporators. And that's what the evaporator is. Inside this, what is coming in is a subcooled liquid or a saturated liquid at best. And then it gets heated up in the process of cooling the room or cooling the space. And because of that, that liquid ends up, or a liquid vapor mixture gets heated up. It's a wet mixture which comes out, gets to a dry saturated vapor. Then it gets further heated up a little bit, a slightly superheated vapor, then it leaves. That's how we get the cooling process in refrigerators and air conditioners. And the third process is in chip cooling, and I'll show you a picture of that. And this is a very futuristic type of a chip that is coming out, where right now, when we say we have an 8-core processor or a 16-core processor, we have a processor on which physically there are so many cores. This has got its own limitations, and what people are looking at is, can we put these cores vertically one above the other? It will make the chip much more compact and much more faster, but it requires a lot of cooling. And so here is what they have made this arrangement, and show that. So here is what it is. This is the layer of the processors, microprocessor, the core, which produces the heat when you are running it. And what we have done is we have a small little pump over there, which is pumping liquid refrigerant into this. It boils in this tube, comes out as vapor. Then you cool it in a condenser, and you get liquid back, and it is pumped back into this. So these types of things are being looked at. And these channels, they are very, very small. 50 microns is the width, and you are trying to make this into an onboard micro refrigerator for cooling these chips. So this is what is being done. So that's an example of chip cooling. There's one more application which does not strictly fall in any of these categories. So I'm going to show that in a minute. This is called jet impingement boiling. And what here you do is a surface which is hot, and your objective is to cool this surface. And what one does is that we pump in a liquid through this, it comes out as bubbles, it hits this surface, and this temperature is higher than this temperature, and as these drops move on the surface, there is local boiling taking place. The idea is that since a fresh cold liquid is again coming, hitting, and then moving away, again coming, hitting, and moving away, and there is phase change taking place, then locally in a very small area here, say, you get a heat transfer coefficient which is very, very high. As such, boiling gives heat transfer coefficient which are like 10 times greater than convection heat transfer. Impingement jet heat transfer gives heat transfer coefficient another 10 times greater than boiling heat transfer. So this is a very, very attractive thing for cooling something. Such ideas have been used for cooling chips, where locally you want to do a cooling, and with a small little jet you keep pumping on it drops of saturated liquid, it boils, cools it very fast, and your temperatures come down. So that is one example of chip cooling. A real big example of this was in continuous casting. And what happens here, if you have learned in any of your manufacturing courses, is that we put liquid metal here, it could be say steel, and from there this liquid metal drops down. And the traditional idea is that we take this liquid metal, put it in the mold, make it into a solid slab, and then we take that slab away, take it into a furnace, again heat it up, then you put it into a rolling mill and start making shapes out of that. Well, instead what happens in continuous casting, and this was a process that was invented just after World War II, was that you take this thing coming here and then you pump in a spray of water onto this. So liquid steel is about 1550, 1560 degrees Celsius. This water is at room temperature. So you got water coming and hitting it with a huge temperature difference. There's a lot of boiling going to take place. It will cool this liquid very fast. And as this liquid gets cooled, it falls down. It become colder and colder and finally starts solidifying. At which point it is then becomes sufficient strength that you can turn it and feed it into rollers, and then it will go through a series of rolls, and finally you will get the desired product that you want. This could be a sheet metal, it could be a bar, it could be a pipe, it could be any of the eye sections or channels. But the big breakthrough that happened in this was the understanding of impingement boiling taking place at the surface of liquid steel. And what it did was to revolutionize completely the entire technology of manufacturing steel. It requires significantly less energy per ton than what the older process required. It is hugely automated. It requires very few people to operate it. So the productivity of the steel plants increased by a factor of 10, and old steel plants just had to die. They could not compete with the steel purely because of these two reasons. And at the heart of that was our ability to understand jet impingement boiling. Okay, so those were the examples of various types of boiling that takes place. And when we ask the question, well, do I have an equation where I can solve and get the answer? The answer is clearly no. So we look at each process separately as a research project, develop our own correlations, and those are used in design. So, for example, this chip cooling is this type of cooling is also being used to cool traction motors of electric vehicles. We are hearing a lot of talk about electric cars and electric buses. Ultimately, there the power is provided not by an engine but by an electric motor that powers the axles. That motor generates heat. We would like to cool it, and that is a major challenge in electric vehicles. How can I cool the electric motor? This is one of the candidates that people are looking at. So let's now come to understanding something that has been looked at very broadly. So we'll look at some basics of pool boiling, and then I'll spend a little time on the basics of forced convection boiling in a tube. So these are the only two things I will look at. The others, if you have to understand, you'll have to look up the literature and pick up the corresponding papers on that. So let's look at pool boiling. And remember that in the context of the applications I have just said, pool boiling is a very limited family where directly taking the result and applying it has a degree of risk and uncertainty associated with that. So we assume that the wall is isothermal. Let's begin with that particular case, what we have called in convection heat transfer as the isothermal wall, the T case. So Q dot double prime at the wall, this is what we want to know, and we want to relate it with the convection, the boiling heat transfer coefficient H, which is also connected to a temperature difference, which is the wall temperature minus the fluid temperature, which is the saturation temperature at the pressure at which that process is taking place. Now recall that whether it is the evaporator, or the boiler, or the refrigerator, we are not looking only at one bar, we are looking at a very large range of pressures over which this phase change could occur. Okay, so we have to worry about the pressure at which this process takes place. This difference between the wall and the fluid temperature, we call this as delta TE. E stands for the excess temperature. So this is one part of the story. The accompanying part is that this also has to be equal to the energy taken away from a thermodynamic perspective, which is the HFG. This is the specific enthalpy of evaporation multiplied by the mass flow rate of the liquid being going into vapor, which we call as the mass flow rate of boiling. So m dot double prime in boiling multiplied by the specific enthalpy of evaporation is the heat transfer rate that is coming from the wall, and this automatically assumes that overall the whole system is in steady state. Okay, so this is what is happening. If it was evaporation, instead of m dot double prime boiling, it will be m dot double prime evaporation. That the only difference will be there. But remember, you can recall that HFG is the specific enthalpy of evaporation, which is defined as Hg minus Hf for a saturated state. So what is the relation between these two? And like in convection heat transfer, we will try to see the physics of the issue, what is happening there, and from there we will start getting certain types of correlations, which I will not write down completely over here, but I will post it as notes on the forum that for this particular condition, for under these restrictions, this is the correlation to be used. So there are limited number of correlations we have, and I will present that to you. Those are big long things. We will not spend time just writing it out over here. This behavior between these two in pool boiling is summarized in what is called a boiling curve, or more generally, a pool boiling curve. So what do we have in the pool boiling curve is what we'll see, and then we'll see different regions of this pool boiling curve. Okay, so here I have presented this. That here is a picture where on the x-axis is the excess temperature, delta TE, and on the y-axis is Q dot double prime S, which is the wall heat flux in watts per meter square. This is in degrees Celsius. So here we have the boiling curve, which has got relation between these two parameters. This side is delta TE, that is T wall minus the T fluid temperature or the T saturation temperature, whichever way you want to look at it. And this side is Q dot double prime at the wall. We have been using lowercase, so we'll stick with that, Q dot double prime at the wall. And as I was showing the curve, there's one thing to notice in this, that this axis, the way it has been plotted, is a log axis, logarithmic axis. So here you will get, say, number like 10 to the power 3, and then you have, say, here 10 to the power 4. Here it is 10 to the power 5, 10 to the power 6, 10 to the power 7. Very, very large numbers. And what do we have on this side? This is also logarithmic scale, delta T of 1. Then you could have delta T here of 10. And then you have 100. And there you have 1000. And this is in degrees Celsius. This is in watts per meter square. And this curve is not something which is universal, but this is for a particular fluid, and what we are looking at is that the fluid in this case is water. Okay, there is a question there, so let me just take that question. In evaporator, is there any pressure change during boiling? Okay, there is a question said that I have just shown the picture of internal post-convection boiling. So this is boiling in a tube, and we will look at it more detail in a few minutes. That when incoming is a saturated liquid, and what goes out of this, or not saturated liquid, but also what we call a wet state. And what comes out here is a superheated vapor. That means from inlet up to a certain point, you had boiling. In thermodynamics, we assume this process, in the first course in thermodynamics, we assumed this to be an isobaric process. That was an idealization. It just helped us to solve the problem quickly. In the real world, yes, there will be a small pressure drop as the fluid goes through the tubes, and we would also be interested in finding out that as heat transfer takes place, how much is the pressure drop in the real case. So, isobaric phase change or isobaric boiling or condensation, as I have mentioned, is an idealization. In reality, there will be pressure drops. Okay, so that's the answer to the question. So we are going to make this plot and see what is it that happens in this. So here is back to the real thing where you have actual numbers and things put up, and we see this shape, and we will go back and look at this individual parts of this thing. First, we have this point comes up to A, and then it goes up to B, and then it reaches C, which is a peak. Then this thing comes down to D, which is the minimum, and then again it increases. So the question is, well, what is happening? So we'll look at each one of these regions, 0 to A to B, B to C, C to D, and then here and then here. And say, well, in the real case, if I look at what is happening in the boiling process, what will I see? And from there, we will get an idea why we are seeing what we are seeing over here. So we'll start with the first part. So I'll just draw it here. So from here, roughly till about here, we have A. So from here to A, that means if you had a state where the temperature difference between the surface and the wall was 2 degrees 5 something, and all the way in this particular case for water, this is coming to say 5 degrees, then what will you see? So let's look at that part. And what we see there is, so we are coming up to A. That means delta TE is less than about 10 degrees Celsius for water. And what we call this region is called free convection boiling. So what happens here? So take that same vessel that we were looking at, and this is probably something you can see even in the kitchen. If you have this surface and this is being heated up, so this wall is at TW, and in top of this, this is the surface of the fluid. And we say, well, what happens in free convection boiling? What is happening here is that it's not something that our classical thermodynamics helps us to understand. We have to go to non-equilibrium thermodynamics in some sense, that a little bit of a fluid over here, a fluid element, its temperature goes slightly above the saturation temperature, but it does not change phase. This happens, the phenomena is not equilibrium, but it's a non-equilibrium phenomena. It rises up, and as the pressure keeps decreasing, its volume increases slightly. Then it rises up by buoyancy. Remember, this is buoyancy again. It comes up here, and finally it comes to the surface, and where the phase change takes place, and you have saturated vapor coming up. So this is what is happening in free convection, that there is no bubble formation yet. Some fluid has become superheated liquid locally for a small amount, it rises and then flashes off. So if this fluid was going up, it would also mean that somewhere, to maintain continuity at any point, you cannot have this fluid going up everywhere, because that would violate continuity. There has to be regions where this fluid has to go down also. And it's very difficult to do that in the kitchen, because if you have taken a steel vessel or an aluminum vessel and start heating it from flame, and after a while when the water is boiled and you want to pour it into making tea or coffee, then you can see that as you are turning the vessel down and the water begins to contact this surface here, it starts to boil over there. And it produces all types of crackling sound. And that is happening because when you're heating it from here, these walls got heated by the gases going up here, and this wall here, its temperature became more than the saturation temperature. So when you are trying to pour it, it starts crackling and it starts boiling over there, and you can see bubbles bouncing off and sometimes falling on your hand. So it was the case where the wall itself got hot. So what happens in that case is that along the wall also, the fluid, because of convection, will rise up. So in between somewhere, you can see that water is moving down. And if you want to really visualize this, a very simple thing would be to heat this water and put a few crystals of potassium permanganate into it and see where the streak of that color goes, and it will tell you what type of circulation is taking place in this. It has to happen in order to maintain continuity. So this is what happens in pre-convection boiling. And what happens here is that if you look at the literature, H is proportional to the excess temperature to the power of 1/4 to a 1/3 power. The detailed expression I will give out in the notes. I'm not going to spend time writing this whole thing over here. But this is our first thing that happens, is free convection boiling, which took us in this first part of the curve. So this is what is happening from here to here. This is free convection boiling. Now let's see what happens into the next part. It starts from here and it comes over here and then it comes over there. So we'll draw this curve and it reaches something like 10 to the power 6 at a delta T of about 30 degrees Celsius. So this should be about 30 and this is slightly about 30 degrees Celsius. So here we are looking at the minima and we are looking at this curve over there. And there's a point that has been put here, approximately 10 to the power 5, and we call this as point B. And this was the peak at point C. So B comes at a delta T of the order of about 10 degrees Celsius or something like that. So we'll look at this part. A to B is the next regime where something very different happens. And that is called nucleate boiling. A to C completely, this is called nucleate boiling. Which has got two regions, A to B, which is what is called also subcooled boiling, and B to C, this is, you have bubbles coming to the surface. So let's see the differences between these two. That's our pool, and we are maintaining a certain, this is at saturated liquid, and we are maintaining the surface at a certain temperature. What happens in A to B, which is subcooled boiling, is that at a lower value of delta T, which is why A to B is on the lower range, you'll find a bubble is formed there. It grows a little bit, detaches from the surface, but as it comes out, it sees cooler liquid there. It begins to condense, forms a superheated blob of superheated vapor, comes to the surface, and the vapor goes out. So the bubble does not reach the surface. And if you observe carefully in heating water in the kitchen, you'll actually see this happening. You'll see bubbles coming but disappearing. And so, where did the bubble go? Well, it became a superheated, a little bit of a superheated liquid, and it came out of that part. So this is A to B region, where the bubble does not reach the surface, but at the surface, you do see this phenomena that a small bubble is formed, this bubble grows, then it grows, and at some point buoyancy, so this is now a surface tension phenomena coming in. It is held to the surface because of surface tension, and at some point when the buoyancy overtakes it, it detaches, and then as it goes up, as you saw in that picture, these bubbles take all sorts of funny shapes. They become much more flatter. And there's a reason for that. And finally, they come up. B to C region is where now you have a slightly more temperature difference. So when this bubble grew and detached itself, it was sufficiently big that it could rise, take all those shapes, and finally come and burst at the surface and release the vapor which was inside this. So these are bubbles that contain saturated vapor. They transport the saturated vapor up and burst. And what this bubble movement does is that as it moves up, it keeps causing the fluid around it to come behind it. So it gets the fluid coming in here. So there has to be a flow that is going there and coming there. So this bubble is moving up and it will induce a downward flow and set up a circulation, which is something like this. And for that, one looks at the dynamics of the bubble, that as the bubble goes, what does it do to the fluid that is there. So now the bubbles of vapor have reached the surface, broken at the surface, and start throwing out vapor. If you have seen boiling taking place in a pot, you'll find that not only vapor is coming out, but sometimes small droplets are ejected from the surface, and because of gravity, they then fall back. So that takes us to the region A to B, subcooled boiling, and B to C is full nucleate boiling. But both these phenomena together, A to C, these are called nucleate boiling. And for this entire region, we have a complex dependence on various properties of the fluid. And I've just written the formula here, and we'll try to see what does this formula tell us. You have on the left side is wall heat flux, Q dot double prime at the wall. This is equal to mu F into HFG. Mu F is the viscosity of the saturated liquid. Same thing that we saw in thermodynamics. HFG, same thing. And you have one parameter, G rho F minus rho G upon sigma. And you can see here that this is somehow telling us what buoyancy is doing, and this is telling us what surface tension is doing. There is some sort of a ratio of these two forces. It is raised to the power half. And then you have yet another term here, which is Cpf into delta Te. So this is the constant pressure specific heat of the liquid multiplied by the excess temperature, some sort of an energy type of a term, divided by CSF multiplied by HFG into Prandtl number to some power. So this is telling us some sort of energy taken to the ratio of what is something like phase change related energy. This is a constant that depends on the nature of the surface. Prandtl number is the Prandtl number of the liquid. So that's how we get this relation. It is whole thing to the whole thing cube, and that's the type of a complex relation which is valid for pool boiling in the nucleate boiling region. So it tells you that as delta T increases, Q dot W increases. So that is what you are seeing. In the earlier case where you had pre-convection boiling, delta T was increasing very weakly. So the slope of that curve was relatively less. So let us spend some time now looking at this thing, which tells us what is the nature of the surface and how does it affect boiling. So what we have looked at is that here was the vessel at the surface of which this boiling was taking place. Now I can suggest to you to do a small experiment, and you'll see something very strange happening, that if you are heating water in a pot, and at some point it is just about to boil, some few bubbles have started appearing. At that point, you take a teaspoon or a tablespoon of sugar or maybe even salt and put it in this water. And you'll see a very funny thing happening. Or if it's not that, you can even take a little bit of sand and put it in that water. And suddenly you will find the whole water boils for a few seconds and then again sits down. What happens there is that when you drop those things into this water, these are particles that will come and settle down. In the case of sand, they will not dissolve, but if it was sugar that you poured, the sugar particles will come there and sit there, or the salt particles, they will sit there. they form small little roughnesses at the surface, and these small little tiny roughnesses, this is what is called a nucleation site. And this is the nucleation site at which suddenly, where boiling was taking place only at 2-3 points, and that too maybe subcooled boiling was taking place, suddenly you start boiling and bubble formation happening all over the place. So this whole vessel suddenly bursts with a lot of bubbles, and they all come to the surface. If it was salt or sugar, in a second, a couple of seconds, that sugar or salt dissolves in the water, the nucleation site disappears, it reverts back to what we were seeing happening, and you again take its own sweet time to get boiled up. If it was sand, the story will be different, because now these little particles will stay there, they are not dissolving in water, and you will see that there will be a lot more bubble formation taking place in the case when the surface becomes like that. This is one thing that you will see. The second that you will see, that I showed the picture also, that the bubbles that were rising from very specific points in that vessel. And if you very closely observe, every time you boil water in that vessel, bubbles only appear at that particular point. So why does that happen? What is happening is that this surface, for boiling or phase change to take place, you need what is called this nucleation site. This could be a micro roughness on the surface, it could be a small thing up over there, or it could be a little cavity in the surface which is like this, and that cavity could have any shape, doesn't matter. What this cavity does is that locally you have a very large heat flux, and that is where nucleation and the bubble formation begins over there. And that's why the nature of this surface makes it so very critical of where the boiling will take place. If you would like a very large heat transfer rate, then the objective of the designer would be to make lots of nucleation sites on the surface, either this way or by putting a roughness there and put a roughness there and put a roughness there and things like that. So either roughen the, you have to basically roughen the surface by either making lots of say small micro ditches or grooves or something like that, or attach a little bit of these little roughnesses to the surface. That's a challenge on the manufacturing side, and if you can do that, we get much higher heat transfer rates. And many of the tubes that we see these days, the applications, refrigerators or even boilers, they do have these features which enhance local boiling, and they encourage nucleation to take place by artificially creating these nucleation sites. A practically manufactured surface has a certain roughness, but it is not 100% smooth ever, and over a period of time you gradually see these things happening. And the other thing that it does is, because locally the heat transfer is high, the temperatures are higher, this nucleation site will continue to wear out slowly. It will cause failure of the material at that point. And that's what happens in power plant tubes, where at one point where there's a lot of nucleation taking place which was not expected or controlled, then that is where the tube thickness will slowly keep decreasing. Internally it is pressurized, at some point the tube will burst. And that's a very common occurrence in boilers, in power plants. So what we are seeing in this whole new process of nucleation boiling is a very important thing, which is how to get this nucleation things coming in, or how do I control it, or can I predict it? It is the same issue that comes in boiling water reactors, where if you have boiling taking place on the outside of a tube, and where the bubbles will be formed is where there is a nucleation site, and gradually that is the site which will get eroded, and you will see another reason why that will happen. And that is where the fuel rod of a nuclear reactor could weaken, and you would like to know it as quickly as possible and probably take it out of action before it fails. So nucleation, surface finish, these are very important things that are connected to nucleate boiling. Okay, so that takes us to this point where you have a peak happening there, C, and this is called in the critical heat flux. Why it is critical? We'll come back to it in a little while. But for now, let's understand why it has reached a peak. And that is given by what we have just seen, is that when nucleation takes place, more and more bubbles get formed. Gradually, more and more sites come up where more and more bubbles are being formed. And so now, as delta T increases, the number of nucleation sites is increasing, the rate of bubble formation is increasing, heat transfer coefficient is increasing, and finally you have so many bubbles being formed here that this is the rate at maximum way in which energy can be taken away from the surface. What will happen if there are far too many bubbles is that, like in this case, say a bubble was formed here, a bubble is formed there, a bubble is formed there, then if the number of such bubbles goes too high, these bubbles will join up and form a big volume like this. It is no longer looking like a bubble, but it is a two-dimensional thing which is flattish, and this is what we call a vapor film. And once the vapor film is formed, the bulk vapor starts to come into play. It reduces the rate at which boiling can take place because vapors are poor conductors of heat. So these bubbles will form, they may join up, and at the surface itself, you could have a film of vapor. And as we have learned in convection heat transfer, liquids have much higher heat transfer coefficient than vapors. So now in this portion where the surface was blanketed by a vapor film, heat transfer coefficient goes down, while somewhere else bubbling was still taking place. So overall, the rate at which boiling takes place has come down. And that is the reason we see this peak coming up into play, that after this, the film starts to form, a vapor film, against lots of broken bubbles, and that is why it has reached the peak. Why it is called critical, we will look at it later on. Right now I'm looking at the isothermal wall, and so that's what we are doing it. In a minute we will come back to the iso heat flux wall, and then you will realize why this word critical comes into this into the name of this point. Okay, so we have reached this point, and now let's see what the curve tells us. That from this point onwards, from C to D, it reaches a minima where the heat transfer coefficient has started coming down. The temperature, as we keep increasing the temperature of the wall, the rate of heat transfer keeps coming down. That exactly the opposite of what was happening over here is now happening over here. So let's see why this is now happening. So this is this curve which we have to draw. This is now coming down, and it comes down, say, somewhere up till about here, and reaches a minima before it starts to go up. So let's first see what is happening in this region, in this part. We have already seen a little bit of that the film formation had begun to take place. So the vapor films were coming in. As you increase the temperature of the surface more and more of this surface gets blanketed by the film. So now the surface is at some point in contact with the film, and then suddenly it gets in contact with the liquid. So here is what is happening. That's the surface, and we have here the liquid free surface over there. And what we are saying is now happening is that in the initial part of this curve, here is what was happening, that you formed a vapor film there, but here there were bubbles rising there. This film would break up and then start moving up, and maybe it may further break up into pieces, and this will go up. And as soon as this detaches, another amount of liquid comes in contact with the surface, and again it begins to form a film. So this part of the surface gets a smaller film, gets a bigger film, it breaks up and goes up. Another film is formed. So that's the transitory nature. The shape, size, and the rate at which these bubbles disconnect and go off, this is fairly statistical and random in nature. But bubbling frequency may not be random. You can see that there's some periodicity with that. But the shape of these big blobs of vapor, one cannot predict what shape it is. It's very irregular. It keeps breaking up. It could join up. All sorts of things happen. They will rise up finally to the surface and throw the vapor out. As the wall temperature increases further and further, more and more of this wall begins to get blanketed with vapor. So this vapor is formed very quickly. It rises up. Another liquid comes there somewhere. Again, it immediately forms a bubble, vapor, film, and it grows up. And maybe these two join up and form a bigger one. So the fluid, the surface now is increasingly seeing itself in contact with vapor, whereas when it was nucleate boiling, it was largely in contact with liquid, and occasionally when the vapor formed, it would break off and go away, bringing in more liquid in contact with the surface. So more and more of liquid was coming in contact with the surface. Here that is being hugely impeded by the formation of the film, and that's the reason heat transfer coefficient has gone down, because H in general with a liquid is much greater than H with a vapor. And that is what is the reason here. More and more of the surface is seeing vapor blanketing, heat transfer coefficients are going down, and in this case we are also seeing Q dot double prime at the wall is going down. So this is what is happening, and it reaches a point where these films have become so big that they blanket almost the entire surface, and for very large periods you have very large films being formed, and now the heat transfer rate has become really poor. And that is the point which reaches the minima over there, and this is an important point named after the scientist who discovered it. It is called the Leidenfrost point, and this is where you see a Q dot double prime is a minimum. The critical heat flux is a point where you had Q dot double prime was a maximum. So just to give an idea what the maximum minimum things would be, so let's say that the critical point for water is about 10 to the power 6 watts per meter square. So this is 10 to the power 6 watts per meter square, and the temperature difference in this particular case here is of the order of about 30 degrees Celsius. So you put that over there, and this is the value of H at the critical heat flux point. This tells you that this is of the order of, say, 3 into 10 to the power 4, about 30,000 watts per meter square per Kelvin. 30,000 watts per meter square per Kelvin, and water in forced convection you will be getting 1,000, 5,000, 8,000, maybe 10,000 watts per meter square Kelvin. What you are getting here is something 10 times bigger than what was happening, and that's the reason why, whether it is chip cooling or many of the other applications, you want to exploit boiling as a technique for heat transfer. With vapors, that number comes down to hundreds in forced convection. So 100 for vapors, thousands for liquid, and tens of thousands for boiling heat transfer. That's the order of magnitude you are seeing happening in the case of, say, water. So this is one thing that is happening. And in this Leidenfrost point, we have reached a minimum, and the minimum has happened because now the surface is hugely blanketed by vapor. These vapors are now no longer spherical. They are very irregular in shape. They break, they join, they reach the surface, and they start throwing out vapor into the free surface. So that's the reason why we saw that minimum happening, and we said the minimum will happen when this whole thing is very badly blanketed by a film. So that means very few amount of the liquid actually comes in contact with this. And the moment it comes in contact with this, the temperature difference is so high, it becomes a vapor. And the reason why it blankets this thing is that, if you recall thermodynamics, when we looked at Vf, which is a specific volume of the liquid, and compare it with Vg, specific volume of the vapor, this is a factor of 1,000 type of a difference. Which means that if you have 1 millimeter cube of a liquid, which is a tiny little drop sort of a thing, it becomes vapor, you get 1,000 millimeter cube. The volume increases that much, so the 10 times more is 1,000 times more volume that it is occupying, which is why this vapor, although it looks big in size, in terms of mass, is very small, and the rate at which mass was converted from liquid to vapor multiplied by HFG, that becomes small, so the heat transfer coefficient becomes small. That's what we are seeing happen over here. In the next situation, something else is now happening. From this point onwards, when the surface becomes hotter and hotter, and this is the type of thing we would say, power plant boiler tube or something like that, 500 degrees Celsius is the surface temperature. Then again, heat transfer rate begins to increase, and now here 2-3 different things start to come into play. Before that, I'll just put out here the term for the lead and frost point. This is that heat flux rate Q dot double prime at the wall at the lead and frost point is rho g into HFG, and it is a product of G sigma rho f minus rho g upon rho f plus rho g square raised to the power 1/4. So what it's telling us is that for a given fluid at a particular pressure, remember this is pressure dependent, the lead and frost heat transfer flux is fixed. And from there you can then work out what is the temperature difference at which this will happen. So this is the expression for the lead and frost point. The C2D, which was the transition point, which is partially nucleate and then finally it becomes an unstable film boiling. That is what I just explained. And D was the minimum point. Now as you go from D and further go forward, we get what is called film boiling. The surface now no longer sees any drops or bubbles. This is all a liquid, and here you almost see continuously is blanketed by vapor. As soon as the vapor breaks and goes off, little bit of liquid comes in contact, it goes from liquid state to vapor state, 1000-fold increase in volume, immediately blankets the surface. So surface almost always sees a vapor blanket on top of that. This is why it is low, but then as temperature goes up, the other mechanisms of heat transfer come into play. With the rate at which the film breaks slightly increases, so that gives a slight advantage, but a little while later radiation starts to come in. That means from this surface radiation now happens to the liquid surface over there, and this is happening because of differences in temperature. If you see in this part, the end part of this, we're looking at temperature difference of 1000 degrees Celsius, 800 degrees Celsius. Very large temperature differences. There's radiation taking place, and that is what is causing this increase to take place. So what you are seeing here is that you do get similar types of heat fluxes with 1000 degrees Celsius temperature difference, but at this case you got similar heat flux at only about say 25-28 degrees Celsius. And that was here you had nucleate boiling, that was very nice for us. Here you got film boiling, which was not such a nice thing. Okay, so this is what is happening in this curve, and this particular whole curve is called the boiling curve. Relations are available for all these. You can pick up from the book, or I will pass it on in the notes. This is all taken from published research papers. In the case of film boiling, Nusselt number is this function over here. This is G rho f minus rho g into HFG prime, which is like modified version of HFG, mu g kg upon Tw minus T sat d cube. So if you look at this thing, d cube and HFG coming here, or G into rho f minus rho g and mu in the denominator, it tells us, this is something to looks like Grashof number that we looked at yesterday, where we had a length parameter cube multiplied by G and density and viscosity coming in there. So this is in some sense, if you want to convert it to a non-dimensional thing, you say that this is sort of a buoyancy type of a driven phenomena, and also finally you can add on to it later on the radiation part of it. This is not for the radiation part, we will have to add the radiation separately to this. So that's what film boiling is, formula for film boiling. Now let's come to the question as to why this point is called the critical heat flux. Now what was happening in the isothermal wall case, as the wall temperature kept going up, the heat flux will also keep going up. There was no danger as such in the fact that the wall temperature would go up, and that is where a dangerous situation arises, whether it is a boiling water reactor or whether it is anything else. And this happens when you look at the other counterpart of this, which is when Q dot double prime at the wall is produced by, say, a constant heat flux case. And how do we get heat flux case? It is very simple that if you have an electric heater immersed in this, for instance. So in the pool, we put in an electric heater, or we hold a small wire into the pool and say that this is the pool that we are looking at. That's the pool there, and this is the saturated fluid over there, and this is electrically heated. So this wire need not even be that it is like this, but we could take this wire through and through and pass a current through this. Or another example is we have a nuclear fuel rod from a nuclear power plant. Here it is reactions are generating heat. So what boundary condition that we have in this case is that you have a volumetric generation rate of a certain amount, and so the surface sees Q dot double prime wall as a constant. So this is an H case. Now let's see what will happen in this case. Let's assume that we maintain the same heat transfer rate in the wall. So whether this electric heater is there, we maintain a constant current through this, or this wire is there, we maintain a constant current through this. What's going to happen here, and also in this case, although it's a vertical orientation, is that when nucleation sets in, it will start forming some bubbles there, on bubbles there, all around the tube. Bubbles will come, they will keep getting detached and start moving up. As the temperature goes up, the bubbles will get bigger and detach and move up. So the bubble diameter will start to increase, and the rate of bubbling, that is the number of bubbles per unit time, this will also start to increase. So both of these happen as long as we are in this part of the curve. So you are increasing the heat flux rate, you are getting this temperature. You are increasing this heat flux rate to this point, you will get this temperature, the average temperature of the wall. And it is not, this curve is the same for the constant heat flux case. Though the wall, because of the random nature of the nucleation and bubbling process, the wall will be at an average, same average temperature, which would have been if the isothermal wall case had been there. So T and H in pool boiling are the same, unlike convection heat transfer that we learned. So more and bubbles begin to form, and what we have learned here is that as this thing comes here, the bubbling becomes more vigorous, more and bubbles are formed on the surface, and finally we reach the point here, which we call critical heat flux, where the bubbles are so much that they begin to join and they start blanketing the surface, and the temperature difference is so large that as soon as the bubbles break, liquid comes and again it forms a bubble on it. A sort of a continuous vapor film is formed over all these surfaces. Okay, now let's see what happens. If we have a sort of a vapor being formed over this, the surface is blanketed by vapor. Vapor, as we know, has got a much lower heat transfer coefficient than when the liquid was in contact with the surface. So the average heat transfer coefficient will go down. And when that happens, because it's a constant heat flux case, this will be H bar into TW minus T infinity, which in our case is the T fluid or the T saturation temperature. So what this is telling us is that TW minus T infinity, this is Q dot double prime at the wall divided by H bar. H bar decreased because more and more vapor was being formed, which meant that the right hand side kept getting more and more. So H bar decreases, TW minus T infinity increases, or T infinity, this is fluid, TF. TF is constant, which means that TW is increasing. And that's exactly what this curve was telling us, that it is TW is increasing. The moment it forms a vapor blanket on this, the question is what happens to T wall? And here, because we are giving a constant heat flux, what's going to happen is something that does not happen with the isothermal case. So let's see what is going to happen. Is that here you have the same boiling curve now. We have reached this point. This was A. Then this curve was the nucleic boiling curve. And we are electrically heating it. So we are going steadily up along this path. So we got here and the delta T became this much. Now if you increase Q dot a little bit, the surface is already blanketed by vapor. So what will happen is it will jump from here and reach this point, and the wall will reach this temperature. So suddenly, for a very small increase of heat flux, wall temperature difference here, if you see, which was of the order of like 30 degrees Celsius. So here this would have been like 30. This suddenly increased and it went over here, where the temperature is of the order of 1000 degrees Celsius. If the heater or the wall is robust enough and nothing is happening to it, then after that it will continue on the same curve further on. But the real world is not so nice to us, and what we are seeing here is whether it is an electric heater here, or this is a heating wire over here, or it is a zirconia tube in which the nuclear fuel has been kept. The moment locally the temperature reaches 1000 degrees Celsius, whatever material we have by and large used, and the conductors would probably be nichrome or something like that, either that will burn out or the surface will start to melt and start breaking off, and very quickly this whole thing will fail. So you'll have a very large temperature difference on the wall. The wall material will start eroding, maybe melt also, go off, and from particles, the wall thickness will go down, and finally this thing will fail. And this failure happens when, say, at one point you were having this heat flux, so you were at a delta T of say 29, 28 degrees Celsius, and then you say, well, I'll slightly increase the heat flux and go over here. And if you see that numbers, what they look like, here the heat flux is of the order of like 10 to the power 6, and here it is less than say 10% more. So a 10% increase in wall heat flux is enough to cause it to go from this safe operating condition to somewhere in this region, which suddenly shoots the temperature of the material, causing it to fail. That is the danger for almost everything, and this is how the word came about, why it became the word critical got attached to it. And this peak ended up being called the critical heat flux. Critical because from an engineering standpoint, whatever we were looking at, you have a real danger of failure of the material, failure of the device, and your complete disaster. In the case of a nuclear power plant, this is a terrible situation. This is something we always want to avoid, because if this has happened, this tube material will have worn off. Inside this are fuel pellets which are radioactive. They will get exposed into the water, and then you have a real problem, which is actually called the meltdown. Something like this happened at Fukushima nuclear power plant, and finally that is why in nuclear reactors, the safety part, this is such a very, very important thing. So this is what happens in the constant heat flux case. And let's see what will happen if we do the reverse. That suppose the material did not fail, we started from this condition and started decreasing the wall heat flux. So we came up to this point. And then as you keep decreasing it, because the film surface is there and you have always continued to decrease the wall temperature, that film will start getting weaker and weaker, and finally it will reach the Leidenfrost point. So this is the states that it will follow on the cooling side. So we reach that point because you are coming down this axis, and then if you slightly reduce the heat flux at this point, it will jump from here. So whatever temperature difference was there, it will jump down and come to this point, and now the temperature difference is much lower. So instead of a high temperature difference with sort of a stable film boiling or an unstable film boiling there, it comes here, which is into the stable nucleate boiling pool. Wall temperature decreases, the delta T decreases substantially, and you can see from here what sort of a change would take place. Here delta T is 120 degrees Celsius, but if you take this line over here and then look down over here, you're looking at about 8 degrees Celsius. So you have the same heat flux happening, but with a much lower heat flux. So this is telling us something, that in heat flux case, you can have the same heat flux happening in this case, which say here was 30 degrees Celsius difference and here 1000 degrees Celsius. So delta T, although it is vastly different, it's producing the same heat flux. And in this case, it went down here from 120 degrees C to something like 8 degrees C, although you have the same heat flux. And the thing is explained by the fact that here you had the film, here you had bubbles forming and detaching. So that's the sort of a thing we can get. And for most cooling applications, you would like to be somewhere in this region and say, look, I will try to do whatever I can to produce this, so I get very high heat transfer rates. That's the attractive feature of this part. This is the importance of the safety aspect, why it's called the critical heat flux. So that gives us a complete relation of the boiling curve, and we'll finish it off by drawing this line and say that this is where it increases and then it continues to go up. So that is the basics of a pool boiling situation. Some of this has been done for pools, some of this has been done for horizontal cylinders, a few of these have been looked at flat plates. But by and large, this is experimental data from which we have learned this, and this is limited by what those researchers did. The thing is that this is for one particular material that I have shown. And what happens is that as you start looking at newer and newer materials, then you got to redraw and redo this whole work and regenerate this data and then use that data in engineering design. This is what has happened in the world of refrigeration and air conditioning, where due to climate change aspects, you have to get rid of the older refrigerants like R12, R22, then some other refrigerants came in, and now even they have to be phased out, and you are looking at all sorts of now 134A, and more refrigerants coming in. So, and how old is this? Well, these refrigerants were discovered just after Second World War, so in the 1950s or somewhere in that range. And now we are getting more and more other refrigerants in the products. The next time you go see a refrigerator in the market or an air conditioner, they will have put a lot of things about this and which refrigerant it has and how eco-friendly it is, which means how much it is a damaging effect on climate change, global warming, and what is its effect on ozone layer depletion. Because ozone layer depletion which cause these refrigerants to go out. So now let's see what actually happens in the case of the refrigerant in these type of applications like refrigerators and air conditioners, where in the evaporator we are pumping in the saturated liquid and getting it to boil. So if you just quickly recall, this is the pH diagram. I will just show that one here. So here is a refrigerant R23, and that's the pH diagram that you are familiar with from thermodynamics. Now if you recall, what we do in this case is that we take a certain pressure at which the compressor has discharged the fluid. That is like 10, 15, 20, 25 bar, somewhere in that range. And so this is megapascal, and this is 2 bar, so like 6 bar here. So we have a slightly subcooled liquid at the exit of the condenser. So the condensation process we'll look at tomorrow when we study condensation. And it is this state from where throttling takes place when we come down to some pressure like somewhere over there. We produced a wet state, dryness fraction like about 15%, 10%, 20%, something like that. And then we sent this into the evaporator where it got heated by the warmer substance on the outside, and that thing got cooled, so you got the cooling effect. And then this got heated up, it came out like this. It became a saturated vapor, and then we heated it a little bit more, until it became a superheated vapor, at which point we then send it into the compressor. So this part is the boiling heat transfer. This part is your plain convective heat transfer. This we have studied. Well, let's see what happens over here. The point for putting out this thing is that the entry state into the evaporator is not a saturated saturated liquid, but a wet state, about 10-15% quality. That's the difference. But what I'm going to explain now is we will say, well, let's not worry too much whether it was 10-15% or not. We will see a tube into which at this point we introduced saturated liquid into it. It goes through this whole tube, and this is could be several meters long, and exits at this point as saturated vapor. So we are saying that we are going from x equal to 0 condition at the inlet to x equal to 1 condition at the outlet. So let's see what happens in this. And this is very different from what we have looked at in pool boiling, in that this is now forced convection, internal boiling. Much the same will also happen in natural convection, internal boiling, which is that power plant boiler tubes that I was showing you about. So let's see what will happen here. The liquid goes in, and as it's this surface, TW is greater than the fluid temperature or the saturation temperature. So what it does is it gives us 4 different regimes of what will actually be seen. In the first part of the flow, because of the heating, we will see nucleate boiling and very small bubbles will come out, which will maybe detach or are pulled back because the fluid is flowing through it, and you will start getting bubbles coming in. But as you go downstream, more and more bubbles are formed, and so you get the first regime here, which is called the bubbly flow. Then, as more heating takes place, more and more bubbles are formed, their size increases, and gradually they start joining up and forming a bigger irregular shape type of a void, which is called a slug. So this regime, where you now see these type of things happening, this is called the regime of slug flow. So here you had nucleate boiling locally happening at the surface, and pool boiling just told us that there will be very high heat transfer coefficient over here. Then you have something forming here, and a little bit of increase, but not too much increase. And then after some point, these slugs will become so big that they will occupy most of the volume, and the liquid will now be confined to the other thing as drops inside the slugs. And here we now know that surface is now largely in contact with the vapor, so heat transfer coefficients will come down, and so the rate at which this liquid now, instead of bubbles, we have droplets here, and this is called an annular flow. That means it has reached a point where you have now largely a vapor over there and only liquid droplets inside this. So this is annular flow, and finally when this whole place is occupied by the vapor with little bit of drops, and they are also slowly becoming smaller and smaller in size, this is called as a mist flow. It looks like a mist, the mist flow is there. And finally, all these droplets have disappeared, and all you are left here is saturated vapor coming out. So these are the 4 regimes that happen in forced convection inside. And if you have to plot the convection heat transfer coefficient along this direction, so this is x, and on this side we plot hx, which is the local heat transfer coefficient. Then we expect that from here to here, somewhere here it will increase, and then because mostly vapor is now coming in, it will start to decrease, and then again slowly increase. So we have hugely varying heat transfer coefficients along the length of the tube, and so what length of the tube to actually put is not just determined by the average heat transfer coefficient, but by approximately the portions over which each of these regimes takes place. And really speaking, you don't have an exact point that this is 1.1 meters and this is 3.1 meters or 4.6 meters. This is a continuous movement from this to this, and you can strictly cannot say that this is where the bubbly flow ends and this is where the slug flow begins and this is where the ambient flow ends. So we can't exactly say what the lengths are. So there will be some uncertainty with those lengths, but this is the way in which we will end up doing these things. Yeah. Okay, so this is what is happening in forced convection in a tube flow, and that covers whatever is known about boiling transfer. What we need for this course is pool boiling, the physics of pool boiling, and some correlations for problem solving, and internal forced flow boiling, and some correlations for that. So with that, we have covered most of what we wanted to do in boiling. We'll now have questions. Okay. Okay, so here is the question there. First question is, what is the role of surface tension in boiling? Okay, so let's take that point over there and we'll go back. We have drawn several of these things, including this forced convection in a tube. So I'll just keep this picture here and let's see what happened in the pool boiling case. So this was the pool and we had liquid over there, and we said when vaporization took place, a bubble got formed. Now, whenever we look at bubble, what bubble is it's a interface between a vapor and a liquid. So the surface is governed by surface tension. So this is a central player in that. The second thing that surface tension comes in is that when the bubble is attached to it, say like this, we know that what keeps the bubble attached is the force over there, which is the surface tension between this and the surface. So that's the reason why surface tension is critical in first in formation of the bubble, and second at some point why this bubble will become big and break away from this. That's when the buoyancy and the surface tension will be unequal at that point. Okay, so this is the role that surface tension is playing in the boiling process. The same thing is happening over here. How much of these bubbles will form is dependent by the surface tension of the fluid, how these will form and how they will join, and how that is also governed by the surface tension. So and we saw that happening, that in the correlations, surface tension comes into many of these relations. So that's the thing. Okay.
How heat flux can be linked with
Okay, so the question here is how heat flux can be linked with Leiden-Frost point. So I guess your question is that this expression which has come here. Yeah, this one. So what the question seems to be is that once we say that the minima, why is it constant for a fluid at a given pressure? Well, the thing is happening is that what has happened there is that you got some sort of a continuous vapor blanketing of the surface and nothing else is affecting it. So what you have entirely is the properties of the vapor that are there and how much energy was taking off. So in that sense, because you had a stationary type of a system, that you had a surface on which this was there all the time, the liquid would come at some point quickly become a big vapor. So you are looking at a sort of a quasi-static situation where on the surface you always have a vapor blanket on it. And so once we have decided what pressure it is, everything seems to be getting fixed. And that is why we get that there is a unique heat flux associated with the Leiden-Frost point. And much the same way, there is also a unique heat flux associated with the critical heat flux point. And to continue, since the heat flux is unique, it also means that delta T is also unique. So that's how that point got fixed actually. Okay, so it's not just that heat flux got fixed or it was unique, but so is delta T.
P occurs at 120 degrees centigrade or above.
Okay, the question is, will the latent frost point occur at 120 degrees C for all fluids? Well, it will vary from fluid to fluid. The picture that I have shown is for water. If you have any other fluid that you are looking at, this curve will be completely different. So, but the shape of it will be same, but the absolute numbers at which things come, that will not be the same. One of the difficulties with boiling is, and this question raises that possibility, that if I do an experiment on, say, water and develop all these correlations, can I then automatically extend that to any other substance, say propane or R134A or something like that? Well, the nature of these is that if you can, most of these we are not able to fully non-dimensionalize. It also depends a lot on the surface properties, and so it's a very difficult to say that you can use the same thing for any that we have. Some of these expressions can be generalized, some cannot be. So you'll have to keep that in mind while using it. And even if you do it, as I mentioned, uncertainties of plus minus 50% are not uncommon. So these are relatively this, and that uncertainty comes about because of scatter in the data. That different people do different experiments, they get different points, and the data gets spread on a very large range. So there's that issue with that.
Is there any possible increase in temperature gradient after?
Okay, the next question here is the difference between thin curve. Okay, there is no difference. I have just used the same term. The same curve is there. It's called you can call it either of them. That's not a problem. So what I've drawn and what I've shown is you can call it pool boiling curve or the boiling curve. The reason why I have called it as the pool boiling curve is simple because in forced convection, that tube that I showed you, this boiling curve does not apply there. The phenomena is completely different. Maybe locally something could happen, but still we don't see this type of thing happening there. But yes, if you have a constant heat flux wall and you are pushing liquid into it, then maybe at some point you will get a critical heat flux and you could have a problem over there. Okay, is there any possibility of increase in temperature gradient after leading frost point? If it is so, under which conditions? So the question, is there any possibility of increase in temperature gradient? I am not able to clearly figure out what the question is. So what is happening is, well, what is happening here is that as delta T is increased, we start getting these states. So the temperature is increasing. And if you look, I know what you're mentioning by the temperature gradient. If you are looking at this temperature gradient, well, yes, it is increasing. Okay, is there any pressure change during boiling? Well, okay, this is the same question. Now let's see. I just drawn here what happens in post convection in a pipe. And you can see that you also would like to know the pressure drop in this particular case. And so how do I get pressure drop? Well, all the fluid mechanics you have learned tells you what is pressure drop for a liquid. It tells you what is pressure drop for a gas or a vapor. And those are all nice and beautiful non-dimensional forms. But what happens here? How do I tell pressure drop in a bubbly flow? Very difficult. Pressure drop here, pressure drop in this, pressure drop in this. So the only thing to do is to do a lot of experiments, figure out what is the pressure drop at different points, and from there develop some relation that for this material, for this tube, with this roughness, for this temperature, this is the type of pressure drop you get. Okay. Any other questions? Okay, so let me just summarize what we have done. We started by looking at boiling, and we said there are 4 possibilities, and for each possibility I have given you some examples of engineering where we actually use that. And I've also mentioned that there are some applications where we are actively exploiting boiling heat transfer for cooling purposes, and the newest applications are electric vehicles and computer chip cooling. We then looked at an ideal case, what is called pool boiling, and we saw what happens in that. And we then saw that we generated a boiling curve And from there, we are able to see what is happening with what the relation between heat flux and the temperature difference enforced on it. We then saw why critical heat flux is called critical. What happens when you have isothermal continuous increase in the temperature of the wall? Then what happens? And if there is a continuous increase or decrease in the heat flux? Then what happens? And that gave us the idea of a critical heat flux, which is a very important thing in the safety of the product. We finally looked at a pipe or a tube through which a refrigerant or a material is flowing, which is getting heated up, and we saw what is the physics of that flow and how we can get heat transfer coefficients for it. The detailed relations for heat flux, heat transfer coefficients are there in literature. Practicing engineers use those from time to time, whichever is available. If a new material comes for which it is not available, then you create it. And it has also given impetus to the idea of nucleation and generating surfaces that will produce a lot of nucleation sites. A lot of people looking at nanofluidics are looking at this issue where we create nano indentations or nano imperfections on the surface, nanometers in length or depth, and then that way get enhanced heat transfer from the surface. So all the correlations that are there or relations that are there, I will pass it on in the sheet, hopefully today afternoon, and then you can use that in problem solving. So we'll end up at this point. So we'll conclude at this point.